Yashish ji, over to you, please.
Okay, Mengji. We will start in a few minutes.
ভিপিএন এর যে অডিটিংটার কথা বলা হয়েছিল মালদা পাঠিয়েছিল না
মালদা, হ্যাঁ, ওই পাঠিয়েছিল মানে টেস্টিংটা পাঠিয়েছিল। হ্যাঁ, পাঠিয়েছিল। টেস্টিং এর ডেটাকে একটা ফরম্যাট দিয়েছিল না।
ఏజ్ కదా వాళ్ళకి ఏదో ట్రై చేస్తున్నారు కానీ పాపం ఆయన కష్టపడుతున్నారు.
मेरी कॉल चल रही, तुम लोग ऐसे बोलोगे कैसे? अब मेरा फोन यहीं पे छोड़ देना इनकेस आई नीड इट।
ট্রান্সফার হয়ে গেল ভালো হয়নি বললাম এর মাকে আমি বললাম যে একটুখানি স্ট্রং হবে ও জিন্দেগি
Hello.
Okay, Ashish, we can start.
Okay, sir.
Start कीजिए.
Hello. Respected high officials of Indian Railways, SSCs, JEs, and all other dignitaries. Today, Chemtech has organized a webinar on LTE network and its applications in Indian Railways, in which a team of executives from Messrs. Ericsson Private India Private Limited are going to give the presentation on the subject. I welcome all the participants of the webinar. Now, I will request Director S&T Chemtech, Shri Vijay Garg ji, to address the participants and say few words about the webinar. Sir.
Thank you, Ashish. First of all, very good afternoon to all the respected seniors, my colleagues, my juniors. Today, we are going to have a very, very important webinar once again. That is use of application of LTE networks in Indian Railways. Because as we know that future is LTE only. So today we are having a very highly experienced team led by Mr. Mayank Bhargava, who is going to present about the use of LTE networks in Indian Railways and from Ericsson side. So I request first of all the participants to please mute your mics as well as turn off their video so that we can have a better presentation. किसी तरह की कोई interruption ना आए. So I request कि सभी लोग mute कर देंगे please और अपनी videos जो है वो बंद कर देंगे. So with these words, I request Mr. Mayank Bhargav to please continue with their presentation. Thank you.
Thank you, Vijayji, and good afternoon to all the senior railway officials and officers. And once again, I would like to thank Cantech for providing us this opportunity. And especially, I'm quite indebted to Vijayji and Ashish, who have been in touch with me and literally who have been pressing me for this webinar. We are delighted to share our knowledge on LT. And today I'm joined with my few of my colleagues who have been, participating with me on positioning the LT with the Indian Railways, especially at the Railway Board. And what I will do is I will take the opportunity to introduce them. So today I have Mr. David Rothman. He is joining me from Tel Aviv, Israel. He is the business development head and overall subject matter expert from Ericsson on the railways technology, and is also a part of the ITSI forum, which is standardizing the FRMCS. So David would be one of the key speakers today during the webinar. I'm also joined by Praveen Vadwa, who is the subject matter expert on Ericsson radio solution and the products. So he will also support us. And finally, I'm also joined by Ashish, who is the subject matter expert on the core. And last but not the least, I'm delighted to say that I'm joined by Ms. Shalini, who is expert on network design and optimization. Now that's very critical activity while we built up the LTE network for the railways. And all the key subject matter experts and specialists are available. Please feel free to put your questions and queries on the chat box. The subject matter experts will try to clarify and submit the responses to your queries. If not, we will try to have a Q&A session at the end. So with that, I will take the opportunity to share the screen, and I will ask Praveen to start the presentation. Praveen, if you can please confirm me if you can see the slide.
Yeah, Mayank, am I audible? I can see the slides.
Absolutely, Praveen. You are audible and loud and clear.
Yeah, good afternoon, everyone. Myself, Praveen Vadhwa. I'm a radio solution expert at Ericsson. I will be taking you through some of the LTE evolution in the communication across the years, and then I will be taking up a LTE overview, and then followed by we will have David on board who will be talking about a mission critical network and the railways application, and then railway network architecture, and we will summarize with the references and summary here. Next slide, Mayank. Yeah. So we have seen the communication industry, then how we have evolved across the years. So it's a journey from past 150 years where we have seen ourselves as a generation where we were working around the basically on the wireline network. We used to have a wireline phones at our homes previously, and now we have totally moved towards the wireless technology. And also on the wireless technology, we have seen the evolution happening across the years from the voice towards the data. So where we are sitting today, if you see that 78% of our population is already covered today from the mobile broadband, which we call it as a smartphones. And then there are 19 billion devices almost which are already connected. It's a figure of 2018. Probably this has increased further by when we are sitting today. And now we see the data growth, like you can see here, the way we are using the smartphones and type of applications we are running at home. It's not only having a various video or the voice. Now there is n number of applications which are being running in the network now, and it is growing day by day because of the innovations which are happening in the industry. So we have seen we see that the data growth which is currently there, it is going to take a multi-fold, or even what the expectation is that by 2024 it will increase to 5 times. This is old data. Probably what I see that this is if we are sitting in 2021, and even we do the analysis for 2025, it is showing that the graph is going to have even 5 times to 7 times data growth is going to happen. And if you have go to Google and do the search there, how the data growth is happening globally, it is increasing every year on year. It's almost doubling there. So this is how we have seen the growth, and this is not going to stop, because the evolutions are going to come, because we have seen that today we are running on our smartphones with a 4K kind of a video. It is moving towards the 8K. Now we will see that there is AR, VR, or virtual gamings kind of a handsets are coming. So a lot of innovations happening here in the industry. Next slide, Mengchi. Yeah, so I will just take you back again to the era, right? So if you talk about this slide, there is a generations of technology has evolved, right, from 1G towards the 5G. This G stands for generation here. So initially when we started the communication on the mobile, it was mainly analog communication. It was mainly driven from the voice. It got replaced with the digital communication. Then we normally known it as a 2G, or some people call it as a GSM. So 1990 it's all started. So we have seen ourselves that the deployments globally happening there, and for the next 10 years the GSM has evolved. And then after 10 years there is always a new setup of technologies comes in the industry. Like you can see the chart itself, like it's moving from 2G to 3G to 4G, and the almost time frame between each technology is almost 10 years, right? Because why it is happening that there is a standard bodies which is having consist of multiple groups of operators across the industry, and also the partners, the vendors who contribute and develop the new technologies, or develop give their own feedbacks and generate new evolution platforms there to build a much faster broadband application, and having a lower latencies and more reliable kind of a communication system here. This is again that has happened from started from 2G. So you can see that from 1991 98 we were it was mainly a voice communication, and we had in between some GPRS or edge kind of a evolution started, where we started accessing some kind of a emails, or some kind of a messages started coming in there in the world of GSM. But the speeds what we were used to have was quite a kbps kind of a speeds there, and the latency was very high. So then the next evolution happened towards the 3G. This is also call it as some people call it as a WCDMA, some call it as HSPA, HSDPA. So again, when the first baseline happens from 3G, it was again a voice centric. But yes, there was a data was also clubbed with that, uh, because it was replacing the GSM. So legacy all services has to be maintained. So 3G took over from there, from the GSM. It supported voice. It also started giving a higher throughputs, but it was still on the on all in terms of kbps. But across the years, it evolved towards the mbps. So maximum peak speed of a users could be maybe 10 mbps or maybe 20 mbps in that. But from 2008 onwards, the another journey started, which is 4G, which was the fourth generation. And it is taken up a separate leap here, and where the speeds of single users can even go up to wireline speed of at that time we call it as a ethernet. So ethernet was giving 100 mbps. So it even replaced that kind of a wireline, and or giving a equivalent kind of a speeds there. And the 4G was able to run up to 100 mbps on the air or on the smartphones here. And from there, now when we are talking about 2021, we see that if you see that it is again a new shift is happening towards the 5G. So the platform which is set by 4G is going to now to a next generation, which will have a more faster speeds, even up to 10 Gbps of a speed we will be able to access in coming days. And it will be more autonomous. There will be a more applications. There will be a more intelligence built into the networks here. But specifically today, when we are talking, we are since our topic is about the LTE, so I will just focus about the 4G. In the subsequent slides, I will take you through some of the technology insight into the 4G as well. Yes, so this slide you covers the 3G to 4G evolution. So as I mentioned, that when the 3G started in around 2000, it was named as WCDMA. The carrier size was WCDMA was mainly 5 megahertz. And the code book or the schemes which was access layers which was used was called as a CDMA, which is called wide code book multiple access kind of a technique was yet there. But ultimately, it's if I say in the layman terms, it was a carrier which was multiplex with some kind of a codes, and then it was decoded by the end users, and then it can translate into a particular application or the users for the voice or the data. The maximum speeds with the user can access was only 384 kbps. The uplink speed was also similar. But in across the year, when it ended in it came to around 2008 or 9, it also evolves towards HSPA. People started calling it as a 3.5 3.5G or 3.9G. Somewhere we have also heard in some kind of a marketing from some of the operators in India. So it was giving a speed up to 14 mbps, and uplink speed was 5.7 mbps. But when the LT started, the baseline of LT, if you see that when it took over from the 3G, uh, some people started calling it as a 4G or LT. It is the same name. People just rename it in a different way, or make it understanding as per that. So LTE is called named as a long-term evolution, and it has taken as a long term evolution, because the 5G standards are also supported on the LT standard itself. Only thing is there are more enhancements as coming on top of it. Coming to LT, the bandwidth size of LT is flexible. It can go up from 1.4 megahertz to up to 20 megahertz. So this gives a quite a big flexibility, because if the operators are, or the some communication providers want to roll out a higher speed data network, they can pick up a higher carrier size, hence more speeds can be given. On the in the technology front, they were using LTEs using the OFDMA. I will cover more in detail. In the downlink, in the uplink, it is used by SCFDMA, and the peak speeds in can go up to more than 100 Mbps. If we see the LTE today with the multiple carrier aggregations and MIMO schemes, we can touch even 1 Gbps kind of a speeds there. And similarly in uplink also, it's a very high data rate, even up to more than 50 or more than 100 Mbps of speeds are possible in LT now. Next slide, Mayank ji. Yeah, so I will be taking through you more in detail about the LTE. Next slide. Yes, so let's go and touch some of the basic terms which normally we hear in LT before we jump to the details on the applications, which will be coming in the next part. So if you see that LTE is being, as I mentioned, that there is a body which is called 3GPP, which defines the standards for the technology, and the LTE is also referred to as a 4G. uh, LTE is a primarily all IP network, because traditionally in the GSM or in the WCDMA, there it was all TDM based there on the transport. So we were using kind of some STM1 or E1 or E2 E3 kind of a frames was used, but it was mainly a TDM kind of a setup. While when the LTE started, it was baseline was day one was at all IP. So all the nodes in the complete architecture, all the nodes will be talking to each other on only on IP interfaces. Speeds I have already mentioned. As I said, the speeds can be even more than 100 Mbps. Now with the latest evolution in LT, it can touch even up to 1 Gbps as well. And the prime difference between the legacy and the LTE is the latency. You can see the latency is as low as 10 millisecond, which is quite important if we talk about mission critical application services, where we want to build a network with a lower latency and to serve the application like in railways or in the utilities and any power systems, or maybe in public safety areas. So latency is a very critical factor here. So we will come across this segment later in the slides, and you will learn that how it is beneficial. Then it's a security, which is also very important, because when you deploy the number of sites here in the network, it needs to be ensured that there is a end-to-end security, or the encryptions are built in, so that nobody can touch the network and snoop it into the network and control the network here. So there are securities built in on the radio interface, and also the similar securities are built in across the network from the cellular sites or the sites towards the core network. So that security systems are also in place. Latency I've already covered, and IP is, yes, as I said, it's all IP. And not only this, the IP application, it is also covering the various data, because since LT evolved from the 3G, so as I said, the 3G was also a baseline for the data application. So LT took over from there. So legacy all services of GS of voice and data are supported. Hence for the voice services specifically in LT, there is we call it as a voice over IP, which is primarily driven by the IMS system, so which supports the voice application on the LT layer. And normal internet, we early data services are already there. So we will cover this more in detail when we come to the core architecture. Next slide, please. Yeah. So I will again take you through some few more terminologies before we move further. First is the EU-TRAN. EU-TRAN, or it's called the access network, which is actually having a radio access connectivity, or the cellular sites which are connected to each other. So that is called the EU-TRAN network here. Then there is another terminology which we normally use, it is called EPC, which is called Evolved Packet Core. So all these EU-TRAN, which is the cellular sites which are there in the network, they will be connected to some controller, which is called the Evolved Packet Core. And if we see the entire system, this is called EPS. So EPS is an evolved packet system, which includes the EU-TRAN, which is our cellular sites, which gets deployed across the network. And there is a centralized core system, which is called EPC, and also the users, which are UE, which are accessing the applications there on the wireless. device or the wireless devices. Those are called the UEs here. Next slide, please. Yeah, so as I mentioned, this EUTRAN, EUTRAN is the consist of E node Bs or which are directly connected to the EPC. So this EUTRAN are the cellular sites which you normally see when you move around your area. You will see a lot of towers sitting here. So all these are called the EU, all these sites which are connected either in a linear fashion or it could be connected in a mesh network to provide the complete coverage to the users here. That is called the EUTRAN. And there is a backhaul connectivity which is from their EU trying to talk to each other and or towards connection towards the core also. So when we talk about the core nodes, which are basically centralized locations which are placed there in a central location covering MME and S gateway. So MME is basically a mobility management system where it controls the mobility of a subscriber, because all these EU trends are finally delivering the service to the users. So users which are having a handheld smartphones which are connected to this EU trend, and through that it connects to the MME. MME is basically takes care of the admission control, mobility application when this user move from one side to another side. All these things are controlled by the MME. Yes, there are on some other elements are also there from the authentication perspective, but those are separate, which are not part of EPC. This was one part I said about the control function, and another is a user data function, because the subscribers has to access the various applications, so which has basically translate into a user data. So data is controlled by the S gateway. So there are two type of things which we have to remember: MME and S gateway. So MME is for the control plane, and S gateway is for the user plane function here. And we can also build some kind of a redundancy mechanism into the network, where we can have a pool of MME and pool of S gateway, so that in case of any failure of the control system, the other control system can take over. Hence, that the complete network should have a higher availability. So those kind of mechanisms are also available in LT. Next slide, please. Yeah. Little bit deep we will go into the LT access technology. So like I mentioned, we came through the previous slides where WCDMA, we mentioned that the carrier was multiplex with some kind of a codes, while in LT it does not happen. LT, we just break the resources into small chunk of a carrier. Within that, let's say for example our carrier size is 20 megahertz, we break this into a small chunk of a resources, like you can see here in the green and the blue color here in this on the top. So this is, we call it as a OFDM symbols, and these are kind of a OFDM actually full form is orthogonal frequency division multiplex. So these symbols are kind of overlapping to each other, and they are orthogonal. So one advantage coming is that when we have create two carriers, you do not put any space between them. You also overlap, and then it increases the efficiencies and increases the throughputs also. And hence this is OFDM technique was used in the downlink, in the LT, and in the uplink there is a SCFDMA is used, which is called single carrier frequency division multiple access here, like you can see in the picture here. So two type of techniques: downlink is separate, which is OFDM; uplink is SCFDMA techniques are there. Then LT, as I said, that LT can achieve peaks throughput even up to 1 Gbps. So there are multiple spectral efficiency techniques are used. One is the one very important thing which normally term we use is called the MIMO, which is multiple input, multiple output. So in this case, we can in the MIMO case, normally when we transmit as in a communication system, when you transmit one signal and receive at the other end, if you have you can do the polarization, or you can change the phase of a signal, and then you can have a two separate symbols running on a different phase. So with the different polarization, we can transmit two separate signals from the same from the two antenna ports. So that means that same carrier same carrier can be can provide the double the efficiencies by using the changing the polarization of a signal here. So in case of LTE, this is translated into is called a multiple input multiple output. So from the cell side, we can transmit two separate signals using the same carrier, and at the receiver end, which is the UE end, we can receive two separate signals on two different antenna ports as well. So this we normally call it as a 2 by 2 MIMO, which means two we are transmitting two signals and UE is also receiving two signals. This is very normal terminology used, 2 cross 2 MIMO, because when we go to the further slide, we will see this terminology is being used here. So multiple input means we are sending multiple signals, and output from the UE is also multiple. So two times same carrier, and receiver is also receiving at the two times of the speed. Similarly, there are other there is a 4 by 4 MIMO schemes are also possible, which means that the same carrier we can send four different signals with using four antennas, and the UE can receive all four of them together. So this is called 4 by 4 MIMO. But normally when we use in LTE in the low bands, for example in the 700 megahertz or in 900 megahertz, we normally use 2 by 2 MIMO. We do not use the 4 by 4 MIMO. Then next thing is about the spectral efficiencies. Like I said, LTE is more flexible because you can have carrier size running from 1.4 megahertz to 20 megahertz. How this is advantage? The advantage is that if the carrier operator has got a 3 megahertz small carrier, it can still run the LTE technology. And if somebody has got a 20 megahertz, it can also use it. So that's flexibility comes, and hence it also increases the peak speed of a user also. Like in WCDMA or on GSM, the spectrum chunk was quite small, while in LTE we can have to 20 megahertz. So hence the single user can be allocated 20 megahertz of a carrier, and hence peak speeds can be given to that. Next slide, Mayank ji.
Praveen, just one question.
Hanji.
What is the frequency band that is being used? This is the bandwidth you are saying. What is the frequency band?
Sir, I'm coming to that. So frequency bands are various frequency bands are available as per 3GPP. Like in India, we have 900 right use from 700 to 900, 2100, 1800. These are the special bands which we are using in India, and 850 megahertz is also there.
What is the Ericsson is using? Which band?
Sir, Ericsson is providing a solution from the product. All frequency allocations or the owners of the frequencies are the various operators. For example, if we talk about Airtel, Vodafone, or railways, or maybe like in railways, you are having a 5 megahertz carrier chunk, which is allocated to in 700 megahertz carrier size. So you have a
Okay,
carrier of
right.
5 megahertz. The frequency band or the band is 700 megahertz.
Okay, thank you.
Okay. So as I said that we can have a 20 megahertz of carrier or even smaller carrier size, and we can break them into a respective smaller resources groups. So we define this table, or it is standardized table, that if you use, let's say, 5 megahertz, you get 25 resources, which are fixed resources, and it can be flexibly allocated to the various users as per the need basis here. If operator has got a 20 megahertz, that means more resources are allocated. This is the simple way to understand this. Yeah. Another thing too important to note in LT is that there are two type of frequencies allocation. One is the FDD, which is frequency division duplex. Another is a TDD. In FDD, there is a separate carrier, a separate channel allocated for the downlink and uplink. In a simple terms, the downlink information will go in a separate chunk of 5 megahertz, and uplink information will go in a separate chunk of a 5 megahertz. While in TDD, which is time division duplex, we do not have that flexibility. It is same carrier which is being used at the for the downlink and uplink. So what normally it is done is that we divide this channel into the time domain, and we, for some part of the time, it is used for the downlink information. Then there is a guard period where we shift from the downlink to uplink, and in the another section we give it the allocation resources to the uplink, where the users will send the uplink information. This is how the difference between the FDD and TDD. So in India, the normally or I would say technology itself, the low bands, which is we call it as less than 2 gigahertz, are all mainly FDD bands, while in the higher bands, more than 2.1 gigahertz, all are TDD bands. So as we go up to the higher bands, the carrier size increases, and hence the speeds also increases here. So for example, in FDD in India, journal operator size is having 5 megahertz or 10 megahertz carrier, while in TDD the carrier size starts from itself 10 megahertz. And it can go up to 20 megahertz very easily, because the carrier size itself becomes bigger here. And when this translates into 5G, it can go up to even 100 megahertz also. Okay, so Mengji, can you go to the next slide, please? Yeah, I will take one pause here and try to explain you this slide, because this is quite a heavy slide, looks like. But let's look at some mathematics here. As I said in the previous slides, that there are various carriers which are, or we have a smaller resource blocks which are allocated. So uh, each resource block has got 168 symbols. Like in a frequency, if there are let's say in 5 megahertz you have 25 resource blocks. Each resource block will have various symbols. In the those symbols are the analog symbols which are transmitted over the air. And in a one resource block there are 168 symbols, and which are transmitted over 1 millisecond. So if we translate into a second, it comes out to be 1,68,000 symbols per second. Now each symbol, as this is analog transmission from the cell side towards the UE, this can be modulated. The symbols can be modulated with the different modulation techniques. It could be QPS, it could be 16 QAM, it could be 64 QAM or 256 QAM. Generally we use 64 QAM. 64 QAM is the efficient, is the best suited for the cell site. Even though we can go up to even 256 also, but 64 QAM will give you 6 symbols, so 6 bits per symbol. That means if you translate these symbols into the bits, it comes out to be 1 Mbps per resource block, which means one single resource block will give a throughput of 1 Mbps. And if you use the next technique, MIMO, which is 2 by 2, which means, as I explained earlier, that you can have 2 input, 2 output, which means that same carrier you can be transmitted the with the different polarization and giving you a double the speeds. So with using that technique, you can make it as a twice the speed, which is 2 Mbps per resource block. Now consider 5 megahertz carrier, which is a typical railway application, and where you have got 5 megahertz with 25 resource blocks will be available. So these 25, when multiplied by 2, it gives you 50 Mbps. So uh, up to peak speed of to a single user can be given up to 50 Mbps from the theoretically speeds which we can give. But yes, this is 50, but within that there will be some kind of overheads, because this frame also carries the broadcast information, control information, synchronization information. So those are typically used to control the users, or to inform the users that you are latching to which cell, what is the load information, and all those things. So then that 25% of the overheads are consumed. So effectively the net user throughput comes out to be 37.5 Mbps. Similar calculation we can do in the uplink also. As I explained, the similar thing. The only difference between these two is that in the uplink we do not have MIMO. Uplink is always a one single transmission, because UE do not have two transmission of antennas. While in the from the base station we can still increase the antenna count, but not from the UE side. UE is having a lesser power. It cannot radiate the double the signals. So hence the throughputs from the UE side will be only limited to 25 Mbps, and with 25% of overhead, it will translate into 18.75 Mbps of a throughput. So just to remember, for a 5 megahertz, the effective cell throughput or peak user throughput can be 37 Mbps, and in the uplink it can be 18 Mbps. Next slide, please. Uh, this slide again talk about the similar thing what we have learned in the last slide. Here the only thing is the carrier increases. Like I mentioned, as you increase the carrier, you get more data speed. So here the last slide we learned that it was having 5 megahertz carrier. Here it is 20 megahertz carrier, which means 4 times more carrier size, means more spectrum or more resources are available with you. That means it also effectively translates to more speeds at the in the downlink. So if we multiply that 37.5 approximately to the increase it by the 4 times, so it is also translate to 150 mbps of a speeds here. And similarly in the uplink also, it increased by 4 times, it reaches up to 75 mbps here. Okay, so this was the whole technology. I have just covered a very basic. There is a lot to learn about the LTE. With the shortage of time, I cannot cover up all the things here. Maybe in the in the next time we can cover up more details. But if you need more details, you can search on the internet. It's a lot of information available on the LTE. But now I touch upon the physical site point of view, from real network point of view. Within the network which we call it as the cell sites which are normally deployed across the network is called E node B. And this E node B has got two functions. One function is called one functional unit is called the baseband. Another functional unit is called the remote radio unit. So these two are the prime units which are there. And if you see typically from the site perspective, radio unit is the one which is transmitting the signals from the site towards the UE, and the whole information which is being transmitted or from which is being sent from the towards to the radio unit, it is being controlled by the baseband, which is normally sits inside the enclosure. And a radio unit it's also connected towards the antenna, because all the waveforms which are formed on the air is transmitted through the antenna system here. So three systems which are very important: baseband, radio unit, and antenna. Next slide, please. So as I said in the previous slide, the basebands are mainly typically are sitting in the enclosure. So a typical site layout will look like this. If you have one E node B site, this E node B will have a baseband and radio and antenna. When you start transmitting, it can cover the particular area. The area can be linear, it could be 360-degree. So I'm giving you a very I'm again going to correlating this application from the railway perspective, because will be more helpful for you. So railway tracks are quite linear. So what if we have to design a network on a LT? We can have one base station or station A, where we can have all these three components, and then when we radiate, it can have a uh, uh, either we can have an omni antenna, or we can have a directional antenna. If we cover a omni antenna, we are not going to get any benefit. Why? Because omni antenna will cover 360-degree coverage, and it means that we are losing the power, because on those areas where we don't need to provide a signal, we are unnecessarily radiating in that direction. Hence what we need to do is we need to put a directional antenna, and that directional antenna will send it towards the one side of a track, like you can see from a station A here in the picture. Similarly, in the right side, station B, we can have one more base station or E node B that can be transmitted a signal using the again directional antenna towards the left side of a track. And hence the planning is done in a way that it both these signals overlap each other, so that when the user is moving from station A towards station B, the signal strength from station A will start reducing. At the some point in middle, you will find that the signal strength of B will increase. Hence the user will hand over the towards the station B here. Hence we are able to cover the complete track, right? So that's the basic way of radio dimensioning. And these E node B are connected to the respective core location, and when the user do a handover from station A towards station B, it informs the EPC that okay, now I am in under a coverage station A or under station B here. And then subsequently the users can move from B to C and D and goes on towards the track here. This is a very simple way of planning in the LT network. Again, going to this was a very simple example like I showed, but things life is not very simple here, because the communication in the railways application has to go, your network is not only in the outdoor, also there is an indoor. When we talk about indoor, means it's tunnel. For example, you have to connect all the lengthy tunnels, maybe even to 10 kilometers. Then you need to still, you cannot have a high rise tower and all those things. The tunnel solution has to be separate. So there is a technology available where we call it as a leaky cable, or we can have a small cells per se deployed across the track that can also be used to cover up the entire area under the tunnel. Then the third segment is the in-building solution. Normally you see that in some of our homes we do not get a coverage, or in some kind of a commercial buildings there are separate cables are laid. Those are laid to cover up the indoor signal here, because when you are putting up a site outdoor, sometimes that your signal strength gets weaker, because of when the signal penetrates across the wall, the signal dies down, so you do not get the efficient speeds. So to increase the speeds, we put antennas more close to the user. That's called using the help of a DAS here, which are or the small antennas with low power are put across inside the building here. And across all these things, these all type of variable sites are connected through the basebands and also through the router, because router is required to have a end-to-end connectivity reachability of this communication IPs from there to the network operating center or to the core system here. So this is how the complete architecture looks like. Next slide, please. Yeah, so when we talk about especially a railways application, so because the site solutions are different, because somewhere we have to, in stations for example, we have to cover a provide a 360-degree coverage, or maybe it's a kind of a junction where you are having a three directional legs are there. So we can offer, or we can build a solution with three radios and with three directional antennas, and then all these radios can be connected to a baseband and further to a router here. And these whole systems now are so so leaner that that everything can be equipped into a one small enclosure, which is not having any requirement of any AC air conditioning. It can be mounted anywhere on the track side and without having any air conditioner here, and it can support even temperature ranges up to 55-degree. So all the equipments will be placed inside this, and it is a kind of a secured system where you can have a security aspects as well here on this rack. Similarly, you can see that in the two sector solution, where we are if we are on the around the track here, and you have to cover a linear coverage left and right side, then you can have two sector site or two radios covering the 180-degree, providing a 180-degree coverage. Similar kind of a setup like three sector, only changes the radios. Then there is a another aspect we can do is that to reduce the capex of a system, because we do not need to put everywhere the baseband and the router, because as a system becomes less efficient from the cost perspective. To make it is more efficient, what we can do is that we can use the fiber which is laid across the track and connect this remote sites by just placing the radios there. And to energize the radios, we can have a battery backup and the power system on top of a tower, like you can see in the picture very clearly. These systems are quite compact, and it also provides avoids any kind of threats here, because all the systems are not placed on the ground. Everything is placed on the top of a tower and near to the antenna here. And then these can be just connected through the fiber system towards the respective baseband units there on the track side. So this is one of the unique thing which can be done in the network to make it more efficient, and also more efficient from the security aspect perspective as well. Next slide. Yes, so like I have shown there, so instead of having every site having a separate baseband and routers, we can have a set of 6 sites like I had shown in the picture here. Station 1 is controlling the green color sites, station 3 and station 5, and station 6 is a purple color, which is handling station 4 and station 2. So station in intermediate stations, which is station 2, 3, 4, 5, they are not having any baseband, but they are still creating a creating making they will still call it as a E node B, or they will still have a form a radio cell. Why? Because these radios can be connected through the fiber media to the respective baseband location. Now in case there is any failure, next slide please. So like you will see, if there is any by chance there is any failure, still the coverage across the track will be maintained by 100%. Reason being that even though the purple color sites are not available, but the green color sites are still serving and providing a complete coverage. So this is giving us efficiencies that we are not putting up a basebands and the and the routers everywhere, and we are not building up a very large enclosure an enclosure sites here. We can just put a radio systems, and using with the help of battery backup and power system, those can be put on top of a tower and make the system more efficient here. That's one of the unique thing we can do. Coming to last, RAN dimensioning. So dimensioning is a very critical parameter. It all depends on what type of services which we want to plan. So before deploying any network, we have to ensure, we need to be very clear what kind of a services we are going to build, so that there is a seamless coverage, and the seamless throughput is available across the track. Like you can see that, as I mentioned in the previous slides also, as we go away from the cell site, there is this the degradation in the signal strength. Hence the speeds will also come down, because it's the speeds will depend upon the strength of a signal, and also depends on the modulation. So as you go across the track, your speeds will keep on varying. And like you can see in the chart, the way we have shown that, generally if you see you are near to the cell, you might experience a 5 mbps, and then when you go in between the cell site, you'll find 512 kbps, can touch 512, even though it can be higher, right? And so this dimensioning is based on the principle that what is the throughput criteria we are looking for. If we are looking for higher speeds, definitely the inter-site distance will become lesser. Like in this picture, we are showing 6 to 7 typical 6 to 7 kilometer of a two inter-site distance between the two sites, considering 512 kbps of a downlink speeds, and 64 kbps uplink speeds requirement. But if there is a increase in the demand of a throughput at the cell edge, or I would say, if the requirement is of higher, then surely the inter-site distance has to go less. That means it will not be 6 to 7, it may be 4 to 5 kilometer or even lower. But if you, as you increase the number of sites, it will increase the capex, because more sites means that we are putting up a more number of base stations, we are putting up a more hardware into the network, and that means maintaining the hardware, or it will increase the total overall budget of a solution. So this is just a very basic part from the dimensioning perspective. Yeah. So in the end, I will just summarize. So as Ericsson, we have a complete set of solutions available to offer. We have radios, basebands, and as I mentioned, these are the two typical things which are required at the cell site. Then we also have our transport solution, which is router. And then we, as a site solution, it is important that, because you should be able to house the systems inside the enclosures which do not have a special air conditions kind of a requirement, and it has those site systems are available. And all these equipments which are going to be run on our Ericsson software platform, they will be all managed centrally by our management system. And we also offer end-to-end services also towards the operators here. Yes, as I said in the start, the systems have evolved and it becomes more leaner. Like you can see the picture of a baseband unit. It is hardly a one-use size. It's and it can be housed on the inside the enclosure, or inside any chamber on the rack, 19-inch rack. The radios are quite compact. It can be easily handled and carried from by the person to the top of a tower. And it's a very flexible way of deployment. It could be deployed in a tower, or on a wall, or it's in a bookshelf kind of a arrangement here. And we have as I mentioned, we have a full outdoor kind of a solutions are available, where we can deploy all of them on top of a tower also. Next slide, Mengji. Yeah, so I will end here. As I mentioned, Ericsson, we have a complete solutions. Our systems are quite compact, ruggedized, and they are providing all sort of redundancies to the operators, and they are providing a best-in-class the energy efficiencies, and the software systems are quite rugged, so that it gives the higher availability into the network here. So I will end here, and I will pass on to Ashish.
Hey, thanks, Praveen. Thanks, Praveen. I think I believe my voice is loud and clear, right? So I will be more talking about the packet core, right? With LTE as radio has evolved. Similarly, the core network also needs to evolve, right, to support end-to-end, right? And also, if you see about the various new technologies, even in the core, a lot of new components got introduced. Praveen has touched some of the components like MME, SI gateway, and P gateway stuff, and I will be talking more in detail of these, right? Uh, One of the major is the device, right? The device should support the LTE functionality, so that it can latch onto the LTE network and take the benefit of the speeds which LTE network provides to the end customer. Maybe the next slide, mine. Right. So this is more in detail. I think Praveen touched on, right? He mentioned MME. So all your control plane from the E node V network, right, goes towards the MME, which take care of the control plane traffic. And then if you see, there is another component HSS, which is basically for the provisioning of the subscriber. So whichever subscriber that you provision has to be provisioned into the HSS or the UDR system. And whoever has the subscription, right, that will be served by the serving gateway and the PDN gateway. So these are the two components which takes about the user plane. One of the interesting thing which happened with LTE is control plane has been segregated with the user plane. So from the E node B, the user plane goes directly to the SI gateway and the PDN, right? So, and then there is another component, which is the PCRF, right, which has been defined to maintain the policy control functions into the network. For example, to manage the QoS, what kind of speeds, what kind of QCI values, quality of services that we have to provide at the network level, or at even if you can provision the same at a per customer level, kind of that kind of flexibility this PCRF solution provides. Next one, I think I have a detailed one. Maybe you need to, it's an animation one. Yeah. So, right. Thanks. So eNode B, I think Praveen has well explained the overall functionality of the eNode B, and from the core perspective, it does the MME selection, the transfer of NAS, all those functionalities it do, and also eNode B take care of the direct user plane integration with the serving gateway network, the right side green one. Uh, and on the left side, if you see, we have MME, right, which do the authentication part with the HSS from a subscription level of stuff, right, and also do the control plane section and the paging and the bearer management. So all these functionalities are done by MME, which is more of an upgraded version of SGSN in a 2G, 3G network, right? And then on top we have HSS, as I mentioned. This is basically for storage of let's say the subscriber provisioning, right? What parameters, what basically services that we want to give to the particular subscriber, those are captured in the HSS, right? And on the right side bottom, we have the serving gateway, right? If you talk about serving gateway, then it is more of the first connection from the node B directly of the user plane towards the serving gateway. And then P gateway talks about more of an IP connectivity, right? How the routing has to happen, the lawful interception, the policy enforcement, the DPI functionality. So all deep packet inspection kind of stuff, all done by the PDN gateway solution, right? And PCRF in the last, as I mentioned, will do all the functionality of QoS setup more from a network level, on an individual level, those all kind of flexibilities that we can get from the PCRF solution deployment into network. And similarly, PCRF can also interact with the IMS kind of solution for, like, say, voice over Wi-Fi or a VoLTE kind of call setup or MCP kind of calls. Thanks. One of the important factor in LTE is definitely is the QoS part, right? And QoS, if you talk about what kind of quality of service we want to give to the end customer here, right? Uh, I've tried to put that into a diagram also in the below, right? If you see the green one and the blue one, right? So we have two kind of quality of services. One is the default, right, which is the default bearer, which is you are doing a browsing. It doesn't matter what kind of speed you are getting, and maybe a P2P file sharing kind of stuff. So in this, we give a default bearer QoS to the end customer, so that with the best of the effort available into the network, he gets the respective speed. But then there are certain let's say applications in the network, like in railway and all those, where we want to have a dedicated bandwidth, right, or a better quality of bandwidth, like when you are doing a streaming, or when you're doing a real-time gameplay, or when you're doing a VoLTE call or an IMS call kind of stuff. That's where you do the dedicated bearer QoS establishment. So that's how we define what kind of quality of service we want to give to the end customer based on the services that he is accessing. Okay. Yeah, maybe next slide. This is similar, maybe a better view of what I was explaining in the earlier slide, right? When we talk about the packet core interactive, we can give QCI 8, which is again 3GPP standard defined, which is your default bearer, right? And when we move to signaling kind of thing, we can give a higher QoS, like when we're doing an IMS call stuff, so that uh, the experience of voice call for the end customer is better, right? So that's where we give a higher QoS. Similarly, maybe one more click. Right. So then we also have the application like MCPD where the QCIs has been already defined, like QCI 65 and 67, which is 3GBP defined, right? So all these functionalities we can do with the help of what kind of applications we want the end subscriber wants to access, and what kind of QoS we want to give using the PCRF. So PCRF helps over the GX interface, right? And we can define based on application and all those stuff to ensure a better services to the end customer. All right, this is interesting. I think David, maybe I don't know how many of you have logged in by then, but there was one of the video where David mentioned on the compact solution, right? This is one of the solution that we have, compact solution that we have. You can see it has everything. It has the RAN, the radio, and the core in one of the compact solution. This is basically to manage the lower capacity requirement or a lab trial setup kind of stuff. It's like a pretty small footprint which covers everything. It's more of a private network setups that we're talking, and it is 5G ready system, right? If we go with today with LTE, even this can be further upgraded to support 5G functionalities going forward. So if railway is looking into something into lab setup or initially a quick turnaround time within a 2-3 months kind of time frame, this can be a good start to go with. Yeah. And I just captured further. This is how it looks. It might have couple of Dell servers, R640, and then it can have the baseband, the router, everything compressed into a smaller version of the solution, plus radio, macro radio, and the radio dots. All those functionalities are available. So if the requirement is to do a quick turnaround of a site, this can be one of the solution. Although it comes with its own capacity scenarios, but yes, it can be a quick turnaround within 2 to 3 months kind of time frame. Thanks. I think that's how I summarize on the core. Sorry to be a bit on the quicker side, but yeah, over to you, Mike. And I will take if there is any question on the chat box. Thanks.
Yeah, David. Thanks, Ashish. But yeah, over to you, David.
Thank you very much, Mayank. So let's talk about the LTE network. So when the LTE network is used as a mission critical network for railway, and if it's an LTE network deployed to be privately used by a company like Indian Railways and created for the sole purpose to specify its connectivity needs, is a mission critical network. So this is a mission critical network that is tailor-made for Indian Railways specific needs. Next slide. So what's the disadvantages of using public network for public safety or for railway? So the railway data and the general public data is shared over the same commercial carrier network. And priority or exclusivity cannot be provided for railway users in Indian Railway public networks today. So no means of preempting the network usage. So this often results in network blockage, jams during incidents, and disaster during emergencies. So we're limited in the inability because of the lack of prioritization available in Indian public networks. So the solution is to use a private dedicated LTE network, and this can offer the emergency services like an express lane for the wireless information superhighway. So you have your own dedicated lane on the highway for the railway communication traffic to use. You have your own track to use for your particular traffic. And if there's an emergency, you don't need to worry about having a congestion on the network. Next slide. So cellular technologies enables governments and industries to enhance operations. So we see many different types of use cases which require this kind of high prioritization, whether it's monitoring, hazard and maintenance sensing, surveillance, video surveillance, connecting the trains, remote operations. So we see the possibility of remote control of trains and train control like TCAS. So in Ericsson, we're focused on three specific areas for our mission critical networks. Public safety, which we have quite a few references. Energy and utilities, we also have many different references in the world. And rail and transport, which is just getting started with LTE. Next slide. So why did governments and industries invest in critical cellular networks? So first of all, in the legacy infrastructure, and let's take GSMR as an example. So it's reaching obsolescence. It's a 2G based system, GSMR, a very limited ecosystem and bandwidth. Today, if you wanted to buy a GSMR handset on the open market, there isn't any availability. There are no new manufactured GSMR handsets available. So it's a very limited ecosystem. And the bandwidth is only 4 megahertz wide, or actually in India, it's even less. I think it's only 1.8 megahertz wide. So it's quite small. So it has high operating costs for the amount of narrowband that you get. So to increase productivity and improve quality, improve worker safety and environment, we go to digitalization. And this will also make Indian Railways more efficient, more safe, and to have a more punctual set of services using this digital set of services. Next slide. So what are the basics of a mission critical network? Number one is network availability. So we need high availability as life or business is dependent on the network performance. This means that we create a network which is completely redundant. That means if one radio, one eNode B fails, we always have another eNode B that's adjacent, that's able to cover in its place. If a core network element fails, there's always a redundant core network that can take its place. So we always have network availability and no single point of failure. We don't tolerate that, and we design against that. Coverage and capacity is very important. So coverage and capacity, we provide the coverage along continuously along the Indian Railways railway corridors and the capacity it needs in order for it to get the mission critical services that it needs. That means voice and TCAS. Those are guaranteed services, and we provide the capacity for that. We also provide security and hardening. We provide encryption so that cyber security hackers can't hack the system. And we also provide QS prioritization and preemption. So if there's an emergency call, it gets priority, and it's never subject to network congestion. Next slide. So what do we get out of this? So first of all, we get safer working environment. We get situational awareness. We have better control of using personnel, and we have real-time sensors, and we have continuous train control, TCAS, along the whole LTE corridor. Next slide. So what are the use cases that railways typically use? First of all, mission critical push to talk. And that means that all the drivers and the employees, dispatchers, signalers, they can all communicate with each other on specific groups using mission critical push to talk. And if there's an emergency, the person who has the emergency takes prioritization and has preemption. We see railways providing remote control shunting. That means operating locomotives by remote control in order to build rakes in a shunting yard. A train control is one of the most important use cases, and TCAS will be working over LTE. So this is an important activity to integrate TCAS with LTE and provide TCAS over LTE throughout the Indian Railways network. Virtual coupling allows, and that's more in the future, but the railways are looking into this, let's say 10 years from now, which would allow trains to work synchronously down a track. They would accelerate a whole rake or several rakes would work together synchronously, accelerating and breaking down the line. And this would allow the tracks to be used more densely and to have higher capacity of freight or passengers traveling down the track. Platform monitors used for passenger trains, where the driver has a monitor where he can see all the cameras along the platform. Indian Railway trains are quite long. Sometimes there's 24 wagons. So this would allow the driver to see the monitor through his monitor, a camera pointing to the doors of even the 24th wagon on the train. Passenger surveillance is very important. So if there's an incident on the train, if there's an assault or a fire or smoke, and there's a report, so the control center of Indian Railways can zoom in real time into any particular wagon that's reporting the incident using LTE video. Wayside monitoring and train health monitoring, these are there are sensors that we can establish all along the rail corridor. For example, track temperature or the switch motors, the turnout motors machines. So there are sensors which we can see the health of all the wayside equipment in Indian Railways network. Also on board the trains. On a modern train, there are thousands of sensors on board. We can also monitor in real time the train health as it rolls down the track and get a full picture as it's in motion. Next slide. So railway signaling has evolved greatly over the years. So we started off several years ago with mechanical signaling, where there was a signaling that would push mechanical switches. And then we went to electrical signaling, which used electrical relays. And now we're moving into electronic interworking, where all the interworking of the Indian Railways network is done electronically. And there are sensors like track circuits and balises, which detect the location of the trains and the detection of the trains along the track. When we move to TCAS, we can provide this TCAS over an LTE network. And using LTE capabilities, we can even position the trains very accurately along the track. So we no longer need the balises. We no longer need the track circuits. We can, in the future, we can use TCAS and LTE together and detect the location of a train independent of any wayside infrastructure, only using the LTE network and TCAS. And this would save a lot of money on the balises and track circuits that Indian Railways needs to invest in today. Next slide. So the big advantage of LTE is it provides one infrastructure for all the services. In the past, we've had GSMR, which provides perhaps TCAS level 2. If you want operational voice, you need another network. You need another network if you want to do CCTV or passenger information system. So you're monitoring many different networks, and there's a UHF network as well. LTE replaces all these. You don't need the UHF, you don't need the GSMR. You have one network to maintain, and that provides the capability to provide all the services that Indian Railways needs, whether it's operational voice, whether it's TCAS, whether it's video surveillance, whether it's train telemetry. All these are capable to be done using LTE. Next slide. So what are railways needs? First of all, you need low latency. So TCAS has to react very quickly, under 100 milliseconds. That's our goal in LTE. You can't do that in UHF. You can't reach these low latencies in UHF. But with LTE, we can guarantee under 100 milliseconds of latency. Coverage, we provide and design coverage end-to-end through pan-India throughout the Indian Railway corridors. This includes tunnels, this includes stations, underground portions, cuttings, remote locations, so we can design a continuous coverage throughout the, to provide even up to 5 nines availability, because we provide redundant coverage. If one eNode B fails, we always have another eNode B to take over its place. And we provide the capacity for the TCAS and for the mission critical services that Indian Railway needs. Next slide. So why is LTE important? And what's the advantage over GSMR and other technologies? First of all, it provides better capacity and coverage. It provides a large ecosystem. So there's thousands of handsets that Indian Railway can choose from in its services. It has reliability and low latency, as I mentioned, under 100 milliseconds, and we can provide redundancy. It has a flexible deployment, so we can, if Indian Railways gets another spectrum, we can expand LTE to a new spectrum. If the Indian Railways has an agreement with mobile network operators in the future, we can utilize their services as well. LTE has a very high security, so it has AES 128 encryption and has encryption from the eNode B to the core, so that cybersecurity hackers can't hack the system from outside the system. And it has seamless mobility, so we can move from network to network very easily. Next slide. So versus UHF, if we just go to the right side of the screen, in LTE, we've got 4 megabits per second. UHF only has 25 kilobits per second. Now, UHF has better coverage, 6 kilometers ISD versus 20 kilometers intersite distance for UHF. That's true. UHF has better coverage, but places like tunnels and cuttings are much poorly covered in the case of UHF. We have thousands of LTE devices and only tens of UHF devices available. UHF has no prioritization capability, so I can only use it for one specific use case, like TCAS. I can't use it like LTE, which can do voice, video, TCAS, all on one infrastructure. And LTE latency is under 100 milliseconds, whereas UHF latency can be as high as 400 milliseconds. UHF is limited in the frequency. Okay, LTE has many different bands, and if Indian Railway gets a new band, we can expand LTE as well. So there's no UHF security capabilities, and there is no mobility capability. That means there is no handoff between one UHF radio and another. Whereas LTE, we have complete seamless handover across Indian Railways network. Next slide. I think we've covered most of these things. Things like TCAS over GSMR. Okay, let's go to TCAS over LTE. So LTE can use any LTE band, and the broadcast services, we can use CCTV, IoT. Our Doppler capability is up to 360 kilometers per hour, and even in 500 kilometers when we go to release 17. It has a very high capacity. It's packet switched. Unlike GSMR, it doesn't need frequency planning, and it uses a 128 QAM modem on both the uplink and downlink, whereas GSMR has a very primitive QPSK modem. So it has a much more efficient spectrum utilization. That means the amount of bits that I can send per hertz of bandwidth is much higher, 12 times higher than what's in GSMR. Also, quality of service. I have 17 levels of prioritization that I can utilize for the different services in Indian Railways. Next slide. So in LTE, we also have a service layer called mission critical push to talk. This is utilized by a server in the core that communicates through the LTE network. On board the train, I have the LTE modem and router with the radio modules embedded within. And then I have connection either to TCAS using an IP connection on board the train, or for mission critical push to talk, I have the driver's client, which is embedded in a PC at the driver's control panel. Also, handsets can be, we have Android handsets with the mission critical push to talk client available. Okay, and we can also embed this software within the dispatcher systems. So the control rooms and the dispatchers also have capability to use the mission critical push to talk system. Next slide. So the features, we can do encryption. First of all the calls are encrypted. We can do private calls, one-on-one calls, or group calls where we push the button and we talk to a whole group of people, all the trains in our region or all the trains in the station at one time. We can do one-to-one messaging. We can send messages to a group. We can send pictures or even videos to a group. So if I have an incident, I want to send a video or a picture of a particular incident, I can send it to all the experts in the vicinity to assist. The video calls can be done either private or group calls. We also have presence capability. That means anybody, I know if somebody is logged in or logged out or out to lunch. I can get the location of individuals at the dispatcher, can see the location of all the individuals on a map in real time. Emergency calls are prioritized. And the supervisor, if there's a supervisor, he can override on a group. He has priority to override on a group. All calls are recorded. And we have the dispatch, which is able to communicate also with the system. Next slide. So this is just the picture of the client, which has specific groups, a list of groups, a list of contacts. It has history, and you can either have a hard wired button on the side or a soft key, which is this orange soft key, which you push in order to make a call. So you make a call by selecting the group and then push to talk. Next slide, please. So in the ecosystem of LTE, we have many different railway modules that are available. Starting at the left with the LTE modem router, which is able to connect an onboard IP network onboard the train with the LTE network. So I can connect video cameras, the driver's mission critical push to talk module, the TCAS, and any onboard sensors like TCMS. Using an IP network to the LTE network to the core. We have an availability of using a ruggedized PC to house the mission critical client, but we're also working on embedding that into the router itself to save this the need for this ruggedized PC. The driver can use a ruggedized display unit in order to make the calls and receive calls, get the contact list, enter his credentials, see the status of the call in front of him as he drives. And we have a rail ruggedized handset, and on top of the train, a MIMO train rooftop antenna that is capable of using MIMO on the downlink. On the uplink, there is no MIMO available yet in the current release yet, but in NR we will have that. Only on the downlink do we have MIMO support. It also has a GPS antenna embedded in that rooftop antenna as well. Next slide. So on board the train, we have the onboard modem, and embedded within that is a radio module. We can see that's Sierra Wireless in the bottom left-hand corner, the MC7430. We have a more modern version of that, which even can be upgraded to 5G using a software upgrade. So when we supply this, it'll be 5G compatible already to start. We have a ruggedized handset available, a regular handset available in LTE, and there's IoT devices that work. Here's an example of a track temperature monitor. So if the track temperature exceeds, for example, 45 degrees, there could be a risk of buckling. The train track could buckle. So you need to warn the drivers to reduce speed in case of buckling so there isn't a derailment. So in order to monitor the track temperature, in the LTE network, we can connect a temperature sensor that's connected in LTE. Next slide, please. So what's the architecture? So what are our needs? So we need, for our rail critical applications, we certainly need that. For emergency communication, we need it. And for automatic train control, for the TCAS, we need the minimum is the capacity for that. We also can add performance applications like telemetry. We can add video surveillance capabilities, but we need a sufficient bandwidth for all these services at the same time. One of the solutions is to provide quality of service. So we can prioritize the emergency services and the TCAS over things like video and IoT. So that's the solution that we implement. Next slide, please. So here is just a view of the, we talked a little bit about in previous slides about the LTE network. So in the middle, in the blue background, is the LTE network. You can see the LTE network, which this is the core, okay? In the bottom left, you've got the eNode B, which is the radio, okay? And the rest, it's connected to the core using a backhaul. On the right side, we've got what's sitting in the control center and the signaling center. So that's connected to the mission critical push to talk module. So we have a dispatcher that we connected to with an embedded client talking to the trains using the mission critical push to talk platform. In the green, we've got the TCAS system. So the TCAS system has the radio block center or the station TCAS, which is connected via IP to the LTE network. On the left side, we can see what's on board the train. So on board the train, the first thing is the LTE cab modem, which has the radio and distributes all the services using IP links on board the train. So we have the local TCAS, which is in green, and a mission critical push to talk cab radio on board the train for the driver to use. And we could add also a video surveillance onboard IoT, etc. And that's connected to a rooftop antenna on board the train that provides the coverage for the radio. Now, you can see the different colors, and this is the different prioritizations that we apply in LTE. So we have mission critical push to talk emergency calls. We've got dedicated signaling for the TCAS. So each one has prioritization. These services have prioritization over all other LTE services. Next slide. So the LTE architecture, we can see here an example of train cameras on board the train connected to the modem, and that's connected via radio to the eNode B, and that's connected in the core to the EPC, and the EPC is connected via an IP network to a central control video monitor system. And we could have connections with traffic generators. This is for testing. We add the traffic generators to test the different types of applications so this is an example of a test we set up in Pune, where we were testing different types of applications over an LTE network, whether it's video or TCAS. And currently we have this very similar type of test going on in Hyderabad at one of our TCAS partners, who's testing this kind of application and quality of service and separation of TCAS among the different LTE bearers to ensure that TCAS has the prioritization over all the other services. Next slide. So here I'm explaining how TCAS will work over LTE, and I don't need the UHF network anymore. I can replace the UHF network completely using LTE. So how does TCAS work over LTE? First of all, the locomotive approaches the station, and there's an RFID reader in Belize in the tracks. When it approaches the station, it gets the station ID, and the local TCAS uses a directory lookup to find the IP address of the station TCAS. Once it knows the station TCAS's IP address, it starts to communicate with station TCAS over the LTE network using IP. And the station TCAS will now register that local TCAS and its IP address as under the supervision of station TCAS. Now, optionally, the TCAS will provide, station TCAS can also provide the local TCAS, that newly arrived local TCAS, with the IP addresses of all the local TCASs in the station under current responsibility. So if there's another 10 locos under the same station TCAS responsibility, that new loco TCAS will get the IP address of all the 10 locomotives. And this will be used later on if the loco to loco SOS communications. So using this list of IP addresses of all the visiting locomotives in the station TCAS area, any local TCAS that needs to broadcast an SOS can use that IP list to send broadcasts. Next slide, please. So when the LTE, when the locomotive leaves the station, so the RFID reader at the exit will provide the local TCAS with the next station ID. Okay, and the local TCAS will use the directory to find the IP address of the next station TCAS. So immediately upon departure of one station TCAS, it can already start to communicate with the next station TCAS. So we have continuous monitoring and control along the railway network. There is no such thing as a block section anymore. LTE provides continuous coverage and handoff from one station TCAS to the next station TCAS using an RFI reader. So once it leaves that area, it will deregister the departing loco. Now we can have the position updates are sent until the local TCAS will register to the next station TCAS. Now we can have it that in that intermediate area between station TCAS, it can communicate with both station TCASs. It can do that communication too, and only when it's fully within the next station TCAS will it leave the last station TCAS. So with LTE, we have continuous rail corridor coverage. A local TCAS communicate with station TCAS even in a block section. There is no such thing as a block section. Basically, it can either continue with the last station TCAS, the next station TCAS, or both station TCASs. Next slide, please. So what happens if there's an loco to loco? So while in a block section, the loco will send periodic position updates to the next station TCAS and to the previous station TCAS. And next station TCAS and previous station TCAS will relay the position updates to all local TCASs in the zone of responsibility. So as I mentioned earlier, we have each loco gets its position updates and messages from another loco by relaying through station TCAS. So you don't need to do, if the station TCAS is up, you don't need to do loco to loco, but we can also do loco to loco. So there's another, if we go to the next slide, we have the alternate which is probably the proposal which will be adopted, and that is this method. So if there's an SOS message, they could be relayed by the station TCAS. But I think Indian Railways proposed method 2, where SOS messages are broadcast from local TCAS to all TCAS. No, not using, but using that list. So using the list that we mentioned earlier, the local TCAS. And I think we go to the next slide. The next slide it shows this when the TCAS is down. Yeah. So if station TCAS is down, I don't need to rely even on station TCAS for loco to loco messages. So SOS messages can be sent to each local TCAS via LTE using an IP address list provided by station TCAS. That's the one we mentioned earlier. So if there's an SOS needs to be sent, within a few milliseconds, I can make a connection and send a message to each loco TCAS in the vicinity. So within a second or two, I reached and sent an SOS message directly using the LTE network from one local TCAS to another local TCAS. Because we have continuous coverage along the whole rail corridor, I can always rely on the LTE network to send communications from any loco to any other loco. Okay, next slide. So I want to talk about FRMCS. And as Maya mentioned earlier, I'm involved directly in ETSI. I'm Ericsson's delegate in ETSI, which is the standardization body in Europe responsible for writing the FRMCS. Now we're working on the FRMCS standards. They're based on release 17. But as you can see here, release 17 is not frozen yet. You can see it's only in 2022 will release stage 3 freeze occur. So really, even the basis on which FRMCS is based, which is release 17 LTE, that is not frozen yet. So the standards are still being written, and we can expect the FRMCS standards only to be ready in late 2022. So next slide, please. And many of the so if we can see the target publication dates for the system architecture, it's March 2022. If we talk about the transport, March 2022, the service stratum, which is the mission critical push to talk part, is only in August of 2022. And then there's the GSMR interworking, which is going to be late. It's not going to be ready by that particular date. As you can see in the bottom, Ericsson is involved as a supporting organization in every one of these FRMCS standards. Next slide. Okay, so in Pune and also in Hyderabad, we've had lab setups for TCAS. So on the train side, we've got local TCAS. We have it going through modem router from class, and then we have a local RF system inside the laboratory with a programmable attenuator to simulate handoffs. And yet we can simulate handoffs and trains running even at 120, 150 kilometers per hour. We can simulate that and see how TCAS performs under mobility conditions while the train is in motion, even in the lab. Next slide. So one of the key parts of LTE is to have a QS. So we have a QS setting for TCAS. It's using QCI 5, which has priority level 1, which has a packet delay budget of 100 milliseconds. So we're typically guaranteeing 100 milliseconds latency for TCAS. Okay, and other services will get lower priority. Okay, next slide. So here, I'm not going to go through this. I think about the basic connectivity in the lab between local TCAS and station TCAS, and we have a whole network here in the lab. We have the core, we have the RAN, we have radio systems in order to simulate the whole end-to-end network while in the Hyderabad lab. So we can guarantee that TCAS will work successfully, even under handover situations, under failover situations. What happens if an eNode B fails? Will the eNode B, another eNode B, take over for it successfully, and we won't have any interruption of train traffic, even if there's a radio failure? Okay, so here we've got a situation where we're also looking at redundancy on board the train. So if we have one modem on board the train or two modems on board the train, if one modem on board the train fails, will it take over? If a radio on the wayside, LT radio fails, so we're testing all the scenarios of failovers, whether it's a modem failure or an LT radio failure in the Hyderabad labs. Next slide. Yeah. So here we're testing local to local communication, as we mentioned earlier, using one local TCAS. If the station TCAS is down, will it be able to communicate with another local TCAS without having to need station TCAS, just using the LTE network? So that's something that is also a scenario that's going to be tested. Okay, so we have in Ericsson mission critical networks, as I mentioned earlier, whether it's public safety or utilities, Ericsson leads the market in the number of references. We have about 21 deployments in 16 countries. Their largest deployments we have are with FirstNet, AT&T. So after 9/11, and we're celebrating 9/11 tomorrow, after the 9/11, the United States government invested billions of dollars in upgrading its public safety communication network because that completely collapsed in New York in 9/11. So they have a completely LTE and 5G based system delivered by AT&T, which is one of the largest mobile network operators, using an Ericsson system. So it uses an Ericsson system to deliver those mission critical services to police, fire, ambulance, FBI in the United States. And the fourth reference is important also, Southern Link, which is one of the largest utilities in the United States. They cover Florida, Georgia, Alabama, the southeastern corner of the United States, which has hurricanes and tornadoes every year. And this particular, we needed a very robust mission critical network with no single point of failure that be completely hurricane proof. And they have no outages at all. It's a very robust system, and it survived all the hurricanes that we've seen in the last 3 years since this has been in service. We also have networks in Sweden, in Switzerland, in the UK, Spain, France, Faroe Islands, part of Denmark. They're all use public safety networks based on Ericsson, the same Ericsson equipment that we'll be delivering to Ericsson, to Indian Railways. Next slide, please. So we also have many railway references specifically for coverage. So we are experts also in coverage and in high-speed trains. So in Japan, there's a Shinkansen train, which also goes 360 to 400 kilometers per hour. The passengers have perfect service on board that train, not using Wi-Fi, but using mobile network operator coverage, even at high speed. And we're experts in providing tunnel coverage in many metro systems around the world. Next slide. Okay, Mike, I think it's yours. Or is it mine?
Yeah, David, I've already moved to the next slide, the Finland one.
Okay, so one of our key partners is customers is Elysverkot, which is the public safety agency, communication agency in Finland. So even though Nokia, for example, is based in Finland, you would have expected them to choose Nokia, but no. Instead, they chose Ericsson. They have a network which is called the Virva network. The Virva network was currently based on Tetra, and they needed to upgrade to 4G and 5G by the end of 2025. Now, you should know that the Finnish Railway is also using this Virva network. So this the Finnish Railway will also be using this same mission critical core. In Finland, mission critical and public safety and railway share the same infrastructure. Next slide, please. So, Mike, you want me to take this?
Yeah, continue, please. Yeah.
Okay, so Ericsson has huge momentum in the cloud core. Cloud core means that our cloud is sitting on commercially available servers. There isn't any dedicated Ericsson equipment hardware in the core. We're using Intel or HP servers. So we have in 5G, we have a huge network of about 100, more than 100 5G core trials, over 60 customers, more than 35 live networks with 5G core right now. In 4G, we've been deploying that already for 20 years. We have about 300 networks and 225 live EPCs. And we also have customers using IoT, which is IoT core. This is for sensors and that are deployed in the network. You could have millions of sensors deployed in the network. We also have something called VNF, virtual network function, where we have all the services in specific modules, software modules on a server. And we also have Volta and Wi-Fi calling, where we're capable of doing completely 4G voice. So all the 4G is voice is carried over the LTE network. And if you have a Wi-Fi network, you're out of LTE coverage, we can use the Wi-Fi network to make the call as well. Okay. So in summary, LTE is the way forward, and it's the technology to be deployed for railway use cases. Ericsson has a comprehensive portfolio, whether it's core components, whether it's radio components, mission critical voice components. We have the complete end-to-end network portfolio for that. We have the reliability, and we design it no single point of failure. So no radio failure or core failure will stop a train. We're future-proof. All our equipment is upgradable to 5G, whether it's in the radio or the core, and we're the market leaders in mission-critical push-to-talk, and we are one of the key players in the FRMCS field as well. And we're one of the largest patents in 4G and 5G patents. Okay, I think that's it. I think we have time for questions.
Yeah, thanks, David. Thank you very much. And thanks to Praveen and Ashish. Excellent presentation, gentlemen. Let me try to pause. Okay, I'm trying to see where is my WebEx. The thing is, stop sharing, and I'm looking at. Okay, so let's try to see if we have some questions on the chat box, and if we can try to answer, and if they've not been answered.
Yeah, so Mayank, there are a few questions which we have answered, and few questions I would request David to answer. Let me take one or two
Please.
questions with David.
Go ahead, Praveen. Thanks.
Okay, so what's the question?
David, yeah,
So
David, there is one question. Do you have CNOC/NMS to monitor and address the network components automatically / manually?
So we have a network manager system, which is monitoring all the Ericsson components. So I'm not sure what are the specific.
Yes,
question.
I think the question is also the same. The question is whether we support the centralized network operation center or the NMS to monitor the complete network. And it's a question is about the how is it supported automatically or manually?
So it's automatic. So all the faults and performance is sent to our Ericsson network management system. That can be relayed to a centralized network management system using a northbound interface.
Okay,
And excuse me, I would like to question
We
that.
don't have. Yeah. So typically, mobile network operators typically have a centralized NOC, and that has a high-level network management system, and we have the Ericsson network management system, which monitors the Ericsson network elements, and that relays all the monitoring to the centralized NOC.
So my question is, whether do you have any AI enabled this thing, network repairs, network, what do you say, that suppose one component fails, then other components should take over like that automatically?
Yeah, that's automatic. Yes, as I mentioned earlier. So if one radio failure, there is no need for manual. So let's say I'll give you two scenarios.
Some other component might fail, like EPC or something like that.
Yeah. Okay, let me explain. So first, if we have an E node B failure, for example, so we have coverage from adjacent E node B, that's completely automatic. The UE will just reselect to the new E node B automatically. If we have a case of a core failure, we have what's known as a geo-redundant EPC, and that failover is completely automatic. There is no need for manual intervention for a failover, both in a core or the radio.
Okay, thank you. Means you have some automatic things, maybe not on AI or maybe something else. Okay. My question is answered. Thank you.
Yes.
Yeah, David, one question is how much is the antenna gain of the cab and
Okay, so an antenna gain, cab radio, the rooftop MIMO antenna that I showed has around a 6 dB antenna gain.
Okay. There is another question. Would your cab UE work in the noisy IR cabs?
What's no IR cabs?
Uh,
Where is that? Just a
would your
minute. I don't
cab
see that
UE, the
question.
cab UE, work in the noisy Indian Railways cabs? Then the
And
locos,
in Indian
the
Railways cabs, of course they'll
yes.
work in an Indian Railways cab. So I don't see
The
I
question
don't
is about the
understand the question.
noisy, because if the higher noise is
Oh,
there,
because of
like,
noise,
yeah,
electrical noise.
yes.
Yeah,
No, no, not
I,
electrical noise. This is
interference.
audio noise. Actually, perhaps
Audio noise.
somebody,
Okay,
yeah, yeah,
okay.
somebody should
So
measure.
yeah, so how? Yeah, I understand. So okay, so right now we have high powered speakers that we can apply, so that and I'm not sure how many dB, 80 dB speakers. Usually it's 8-watt speakers. 8-watt speakers are usually used for noisy LT cabs. So we can specify. You tell us what speaker volume you need, and we could provide the speaker that will meet the noise requirements.
Sir, this is for dispatcher or some other body calling to the cab. But if
Yes,
cab is calling to some other body, then the noise, cab noise, will get mixed with his voice, and his voice will become indiscernible. Means not it cannot be understood at the other end. Some call
because of
originated from cab. So
you
what
mean from the
if it is
cab
solution?
itself?
Yeah,
So
call.
you mean the voice of the driver is not
Yes,
recognizable because of the background noise, is what
right.
you're saying?
Because of high background
Okay.
noise. Do you know the
Yeah.
decibel level of Indian
So yeah,
cabs?
so here we need. So we have that. We have a railway push-to-talk handset, and that we need to check that. I don't have a good answer for that. We need noise canceling capability on the microphone. So there should be a noise canceling capability on the microphone in order to in order to compensate for the background noise. I need to check
Yes.
that.
Something like the microphones used in
Yeah.
commenting,
So the microphone I'm using now, I don't know if you can use.
delivering
So
commentaries from cricket matches, like that. You need
here I'm
something like
using
that.
this microphone here. This has noise canceling capabilities. It's a Planstronics. I bought this specially because sometimes I'm working in a noisy environment, background noise in the office, and it cancels any background noise. You cannot hear any background noise. I can play something here. I don't know, and you won't hear.
But I am sure that you might not have traveled in the Indian Railway cabs.
Yeah, we need to check that for the cab radio microphone to make sure that we have noise canceling capability.
Right. Thank you.
Yeah, David, there is a question whether we need routers at all the eNode B sites.
Yeah, so there's always a site router at the eNode B.
Yeah, so David, I would like to add here that every site we do not need routers, because if the wherever the baseband is placed, then only the router is
Right.
needed. Like we
Right.
mentioned, shown in the one of the slide, that we can have a 6 sites, and intermediate 4 sites do not require any router or baseband. Those can still be connected with the using the station A, station B basebands here. Hence, in that case, all the sites will not need a router there. Next question, David, whether the existing GSMR network is compatible with the upcoming LTR network.
So I didn't see that question. Is that near the bottom? Where was that question? LTR. So there's no such thing as LTR. Okay. So first of all, I need to explain there is no such thing as LTER. That concept doesn't exist. We have LTE. It's standard LTE. Now, GSMR networks are planned in ETSI, in the UIC, are planned to be interoperable with FRMCS, not an LTE-based network, but an FRMCS-based system. So and right now there is a plan. Well, the plan from our competitors is to force the railways to upgrade to SIP. we are proposing, and it's just next Friday that we're making this proposal to ETSI using the existing IZIP interfaces that are existing on your GSMR network, using IZIP interfaces into the interworking gateway. The interworking gateway between GSMR and I don't expect that to be ready till 2024. That's something that is only in the FRMCS plan. That's not something we can provide in the first phases. What I would recommend is not needing to interwork with GSMR until later on, until you have you're using lines which actually have GSMR or sharing with GSMR and LTE. So it's not so simple, the GSMR interworking.
Yeah, this is
I
similar
can have a
question.
separate discussion on that. It's quite complicated, but I'd be happy for those interested to have a separate discussion on GSMR to LTE network interworking.
Okay, so there is another question, but it's with respect to FRMCS standards, I believe. The question is 3GPP specification is still under finalization for mission critical application like MCP, TDT, etc., and likely to be completed by March 22. In such scenario, what is the timeline for implementing LT for TCAS and mission critical application over Indian Railways?
Yeah. Okay. So TCAS doesn't need the FRMCS features. Okay. We can use the LTE release 16 and offer TCAS over the regular LTE. We don't need FRMCS to do that. Okay. So we can implement TCAS over LTE, and gradually we can upgrade the network in future years that it's compatible to FRMCS. But there is not, we don't need the FRMCS features in order to implement TCAS. Nor do we need it for mission critical communications. Those are already available in the 3GPP standards.
There is another question related to transport. Why in a single network of LTE it can be used as a LAN? We require routers. I believe they are saying my question. I think the understanding I take it is that the question is that why routers are needed. Can we have just a LAN network over the LTE and then serve it, and why routers are needed everywhere?
Why is a single network of LTE can be used? We require routers, but so as we mentioned earlier, there is a router in LTE at each broadband unit location, right? So we have a site router, and we have routers at the. So there is no. We need to have a network, an LTE network that serves pan India, okay, and only from two core locations. So we have one core location and a backup core location for redundancy, but that's serving pan India. We need to distribute these IP packets all through India. We need to use routers in order to do that.
I think very fair answer.
So what we'll have is we'll have the EPC, or not, we'll have two EPCs, but then we'll have packet gateways, serving packet gateways, SPGs, and two of them for redundancy in each Indian Railway zone. So you have 17 zones. So we'll have serving packet gateways, which are also types of routers in each railway zone. And then we'll have another set of routers at the BBU locations as well.
Yeah, there is one more question. This is related to the China and Japan railway system. The question is that LTE is still evolving for railway critical application like train protection and PTT. Then what is the technology currently being used in China and Japan for the high-speed rails?
Okay, so right now, as far as I know, China is still using GSMR for high-speed rails. Okay, they're still GSMR. They have a plan to make an evolution towards 450 using the 450 band, but that is proprietary Chinese equipment. There is no international standard nor any ecosystem or devices that are not Chinese that will work in that system. So that's completely a Chinese standard and a Chinese developed system. Regarding Japan, so Japan high-speed train uses ETCS level 1, actually. So it uses Belises still. It doesn't even use LTE network yet. More advanced, you should be asking about Korea. So Korea has quite an advanced system that's based on LTE. They have a high-speed train using an LTE network. Very similar to what Indian Railways is planning as well. Very similar system.
Okay, there's another question back to the router. They're saying that whether the routing can be done on IPv4 or IPv6.
Okay, so if we're talking right now in LTE, we can use it in IPv4. Okay, but when we get to FRMCS will most likely be based on IPv6.
Okay. The next question is whether the eNode B to eNode B connectivity is through OFC. If so, how many fibers are required for this? I believe the
Okay.
question is not correct because we are not using OFC. We are taking a routing network. There will be a IP MPLS network like we are discussing here. So there will be a backbone on the through the MPLS network and through where the eNode B to eNode B communication will happen. Next question: what will be the approximate power requirement of an eNode B with baseband and router? Okay, so the it again depends upon the vendor to vendor, but if we see the general power requirement from the eNode B and a radio, considering it is 2 cross 40 watt or 2 cross 20 watt, so roughly with 2 radios and 1 baseband, the power requirement will vary, will be from 500 watt to 700 watt per site. I think there is no more question in the chat box now. I think we have covered all of them.
Praveen?
Yes.
Mr. Praveen, I'm AK Chopra here. I just want to have 2-3 questions to Mr. David about this TCAS.
Yes.
In the TCAS Indian Railway, which I've tried so far, is on the absolute block system, and now they're trying still for the automatic block. And in the absolute block system, it is from the station UHF is covering for 3 to 4 kilometers. When you go for the automatic block, you have to have a continuous coverage for the entire section. Now, in the slides which you have shown, you have said that LTE will cover about 3 to 6 kilometers, provided the line of sight is available. Now, in automatic block, we are going to have.
But
yes,
that's
please.
for one radio site. But LTE has continuous coverage. So if I need to reach 20 kilometers away, if I wanted to reach a loco 20 kilometers away, so I reach the eNode B that is closest to that loco.
No, my question is slightly different. What I'm saying is that since the automatic block will have signals at every 1 to 1.5 kilometers, and there we'll have to put the RFIDs, which will have to be linked with the LT system. So maybe the LT system will be required at every 1.5 kilometers or each automatic block hut, so that you cover that portion effectively. So is my perception right, or or something else can be done?
So LTE has continuous coverage along the railway corridor of Indian Railways. So there is no range limitation.
No, in a block section, say of 12 kilometers, you require LTE requires a line of sight. Am I right?
No, LTE does not require line of sight.
It will cover all the 360 or your directional antennas will be required.
Typically, the intersite distance for Indian Railways will be 6 kilometers. That means we have a site every 6 kilometers. Now, if your radio block section for TCAS, let's say station TCAS, covers, I'm just giving you an example. Let's say it covers 18 kilometers, okay?
Yes.
So that would be 3 LTE sections, 3 LTE cells, or three LTE towers with eNode Bs would be covering that entire radio block section, or that that station TCAS section that might be 18 kilometers long, but they will provide continuous coverage. That means if I have one local TCAS at one edge and I need to communicate with another local TCAS 18 kilometers away, I do that using the LTE network, but I don't use directly local to local direct RF communication. I communicate to the E node B. The E node B communicates to the next E node B closest to that loco, and then to the back to the loco that's 18 kilometers away. And I can do that with 100 millisecond latency.
Right,
There is
right.
no
Now my query comes
latency
is
penalty.
that the RFIDs, which you said, yeah, which you mentioned in your slides earlier,
The RFID readers, yeah.
when the train leaves the station, RFID is red, and when it reaches the station, RFID is red. In between, if you have got automatic signals, I will be providing RFIDs at every signal to indicate that he is arriving at a new signal. So that RFID will have to be linked with the LT. How do you do that?
Okay. So you have RFID readers for identifying the entry, the boundaries of a station TCAS. Okay, that is the RFID readers which I was referring to. You might have other RFID readers which are used in TCAS for identifying particular signals. Okay, that there is a signal there. Those weren't part of my discussion, and those don't need to be directly connected to the LTE system.
Okay. So they can be standalone and they can read off their own.
They'll be connected directly by wireline to the TCAS system via IP directly.
May I add? I am Lalit Mansukhani.
Yes, Mansukhani, please tell me.
Mr. A.K. Chopra, first of all, actually, TCAS has already been working on automatic signaling also. First of all, it had been tested in 2015 June. Automatic signaling territory in Lingampalli, Hafizpet, Sanat Nagar.
Okay.
Okay, and as David was just mentioning, we did not have a separate tower for each auto signal or separate connectivity. In fact, since the existing UHF which has been used in TCAS has got lower frequency, that's why it is able to cover more. It has got more coverage. It has got better.
UHF has got more coverage. Yes, that's true.
Yeah, so it is able to cover the block section throughout the block section, but we need not have connectivity with each block section. And like auto signaling, it has been working on automatic signaling since 2015 itself. Thank you.
See, my perception, Lalit, is that when you install a LT system with the TCAS, you will have to do the survey for the individual sections to make sure that the quality of signal strength from the wireless is available at each and every spot.
Yes,
that
actually, I'm not any expert,
very
but
important.
it has been mentioned that QCI 5 will be having priority 1.
Okay.
Yeah, so the throughout the section, in order to have adequate coverage, that link design and that survey shall have to be done, and that would, I think, there won't be any problem, and LTE would have better coverage, and that LTE experts can further enlighten on this. There won't be any problem.
Lalitji, you're right. Mayank here. Absolutely, you're right. For each and every section, we need to do the route survey and do the network design. And once we commission the network, then we'll quickly optimize and hand over to the railway. So absolutely, what you said is right, that there would be no dark spots in throughout the track side of the coverage.
So one more question for Mr. David. See, in your earlier slide, Mr. Parveen has mentioned, the bandwidth available is 37.5 Mbps for 700 band, which is available with the railways. So with the various items which you mentioned, like video call and other things, don't you think it will be a restrictive item for the system?
Yes. Okay. So right now, what we're recommending as the minimum coverage that Indian Railways specifies for is to supply coverage for driver's voice and for and for TCAS. And it requires at the cell edge about 750 kilobits per second at the cell edge. And this is also redundant coverage as well. Now, as we get closer to the cell center, we can get much higher throughputs, and then we can have bandwidth needed for video as well. Now, we're not designing the network, and it'll be very expensive to design a network based on 5 megahertz of bandwidth, to design it with availability of video end to end. Now, video, you have to understand also, typically has a variable, let's say, quality. So you can have focus in, and even with 500 kilobits per second, you can get an image as well of what's going on, and then you could focus in once you have better coverage. So video is available. I would say it's not always available at the cell edge, but it's certainly available at the cell center. If there are places where you want better video coverage, we can make a more dense coverage, but that would add a lot of expense to Indian Railways.
So this is why my
Sir, you can do it
point
with
was
high
that
power cab radio. Do you have high power cab radio?
So a lot of questions about high-powered cab radio. Now, our LTE follows the 3GPP standard. Okay, so right now in the 3GPP standard today, in band 28, which is the band that you're using, the maximum power of a UE is 23 dB. Okay, 23 dB. That is by the standard, by the LTE standard. Now, there are other bands, for example, band 14, which is used by the public safety agencies in the United States. They got 3GPP approval to use 31 dB. Not only that, the railway industry in Europe for the bands in 900 that are replacing GSMR and for 1900 have also requested 31 dBs. Now, if Indian Railway says, you know, guys, we need 31 dB, we need both together, Indian Railways or RDOS and Ericsson together to go to 3GPP and make that request to change the standard in band 28 to allow 31 dBs to be used. But
Yes,
we need to make the
sir,
case
you
together
are
with
a
Indian
3GPP
Railways.
member. You are a 3GPP
Yeah.
member, so you can help in it.
Absolutely. And we will be happy to help. But unless
Yes.
Indian Railways steps up and says, okay, these are the quantities we need, and this is the case we need, because typically it's the railways themselves or UIC. Actually, Indian Railways is a member of UIC. And on behalf of European Railways, it's UIC that's going to 3GPP to make this request. UIC is also a full member of 3GPP. So it's my recommendation to go to UIC as well and say, UIC, please help. We're a member of UIC, and please help us to, together with Ericsson, to get 3GPP to change the band 28 standard. We need it to support band 31 dB.
Yes,
And we're doing
whatever.
that for India, for railways in Europe. Right now, there are work items in 3GPP on applying 31 dBs for the 1900 band and 900 band for railways in Europe.
Whatever
So it's
needs to be
possible.
done should be done.
It takes time and a lot of effort.
Okay, your subscribers, your customers will not be only Indian Railways, but the whole world railway. So you should think in that line, not that what is the requirement in numbers of cab radio in
Yeah,
IR.
but you have to understand,
Yes.
it's not so simple because band 28 is used by other users as well. Adjacent to you, there might be another 10 megahertz used by somebody else of band 28. Now, it could be that the frequency authority in India will say, no, if you use 31 dBs in your band, you will interfere with the adjacent band in band 28. It's possible.
How one frequency can interfere in another frequency? That frequency is not being used by any other operator. So it is against the
No,
basic.
you have only 5 megahertz of band 28, right?
Right. So my 5
Who's
megahertz is
who's your
my
next door neighbor? Who's your
exclusive.
next door neighbor?
Okay, next door neighbor. See, frequency does not interfere in other frequency. Frequency
Oh,
means
yes.
yes.
Okay,
This is basic thing.
it's
One
something that we
frequency
need to
doesn't
check.
interfere to the
Yeah,
other frequency. Yes.
absolutely.
Yeah, absolutely. So you now got the point. So
No,
that 31 dB will not interfere with any other neighboring frequency. So
Okay,
there is no
so,
technological reason.
okay, absolutely. So we need to go to the Indian Railways, the Indian Frequency Authority regulator, and say we would like to go to 3GPP and ask for 31 dB. Do you have any objection? And then if
They
they have
will
no
just
objection,
follow the
we,
international standards. Indian authorities don't have any other, I won't say much, but don't have any other way than to follow the
okay.
international standards.
Okay.
They don't do
Okay.
any other
We will
thing.
help Indian Railways in all its endeavors to get that approval.
Yes,
Mr. David,
Indian
this
Railway had
was
to
my
do that.
point. He had given lot of information that so many things can be done on this Rickshaw network, and the limitation of the bandwidth is going to be there. So since you are doing some experiment in Hyderabad, my request to you is please see that within the requirements how much can be done, because once you ask Indian Railways, they'll ask everything. So the limitation has to be told to the ICA. This is what can be done. This cannot be done in that 5 megabyte Mbps bandwidth which the IR has got.
Okay, Ashish ji.
Praveen, this is Dinesh. I'm Professor Telecom at Research. There is one clarification. Like whatever the structure which you have said, is actually each station will be providing an E node B, right? And that will be a two-sector site, right? And in junctions, you will be going for a three-sector site. And you have to provide this E node B at almost like every 6 kilometers. So what will happen if one of the E node B fails? I think one E node B will be providing a coverage of almost, it will have a radio system which will provide a coverage of almost around some 6 kilometers or something, right? So what will happen if one of the E node B fails? One E node B which is located at a particular station fails. Do we have some kind of a dark zone where you won't be having any coverage?
Yeah. So Dinesh, we have shown it in our slide session also. Mayank ji, if you can open the slide again, we can clarify better from there.
Yeah, 1 minute, please. I'm just sharing that slide to him. Yeah.
Yes. So, Mr. Dinesh, like you can see, the way the coverage is planned is that the coverage of one site will be hitting the bottom of a other site. So let's say station one is radiating through the radio and antenna. It is hitting the bottom of a station two. Similarly, station three is also radiating and or giving the coverage up till the station two here, right? So same behavior is across all the sites. Now when we go to if there is a failure, let's say every site distance is 6 kilometer, and if one of the site fails or E node B fails, then there is no dark zone. Why? Because as I said, there is a coverage available from the neighboring site. It will be through available to the entire track as well. So this is how the redundancy is maintained here.
Okay, thanks. And another thing is, will you be able to arrange another webinar on LTE test bed? Actually, we would like to set up an LTE test bed. And whatever I think which was done at the HBL premises, that is that you are not using any traffic generators, right? It's only for the purpose of testing a TCAS. Is it so?
No, Dinesh ji, they would be, as I advised you about the XCR traffic generator. Same way, our customer also has been advised to source one and try to do the Doppler effect testing and handovers. So they would also be doing that.
Okay.
Mayank, Mr. Mayank.
Yeah.
Actually, I am having just 4 and 5 questions because आपको भी थोड़ा जल्दी है. So I was just waiting for my turn. My first question is that what is the exact latency in your LTE network, Ericsson-based LTE network?
Praveen.
Have you tested it?
Yeah. So in the test scenario, what we got with the station TCAS and logo TCAS, we have got roughly around 100 milliseconds or less.
100 millisecond. Do you are having any
Or
report
less.
for that also? Can you share that
Sorry?
report as well? That testing report, can you share with us?
So we would be sharing that with the railway board, with the AM Tele for sure, and then it can be circulated. No problem.
Okay, thank you. So it is 100 millisecond, right?
Less than that also we have got it.
Okay.
Roughly
Now
around 50. It varies from 50 to 100.
50 to 100 millisecond, right?
Yeah.
Okay. My next question is that now since we are going for TCAS over LTE, and there are very limited vendors for TCAS over LTE, I think there are only 3 vendors. So whether there will be interoperability issue?
No. So the LTE network is based on 3GPP, as we have explained over the last 90 minutes. And we don't see any problem in terms of interoperability either between the LTE OEMs or the TCAS OEMs over LTE. So absolutely, there's no issue of interoperability.
Means all are working on the same platform, right?
Absolutely.
Whether it is Capsch, whether it is this Nokia, or whether it is Ericsson based.
Yeah, these are all 3GPP based, VJG. So, so they follow all 3GPP standard of release 14, 15, 16. Yeah.
Right. Another question that in our this RDSO based जो specifications हैं for LTE, we are requiring the features like functional based addressing and location based addressing, right?
Yes.
So whether this release 16 version that will be providing both these functional based addressing and location based addressing.
David.
Yes, absolutely. So the release 16 will be supporting that.
Both.
Location-based addressing and functional-based addressing.
Then why
Based
why
on
at all
release
this
16.
release 17 is required?
Because release 17 has a more dynamic based set of features like a dynamic allocation. So FRMCS is going to be based on release 17. That's what I was saying. FRMCS will be based on release 17.
For LTE release 16 is okay.
Yeah, it's sufficient for Indian Railways. It's sufficient to cover mission critical voice and TCAS. Release 16 is sufficient.
Okay. My another question is that there was functional based calling in case of this GSMR. You must be knowing.
Yes.
So whether
Functional
this
based
mission,
numbering, right?
yeah, this mission critical communication that will support it.
Yes. So there's something called functional aliasing, which is introduced in mission critical communications in the standard starting in release 16. And that provides an alias. Instead of the number, you can use an alphanumeric. You can say driver 24 or signaler 26 or station master 23. So you can provide more information. It's not only a number. In GSMR, it was only a number.
Okay. And my last question is, these LTE handsets, these will be vendor specific or these are common? Whether it is
These are
any
common.
network, they can be used in any network?
Yes.
Or they are vendor specific?
Off the shelf. They're off the shelf, commercial off the shelf LTE handsets.
These are any vendor, Vijayji. The way you are using right now a handset, either when you go on Airtel or Vodafone or Jio, exactly the same way it will happen in railway LTE network.
Okay, so it will not be vendor specific, right?
No.
No. So that's why I said there's no LTER. You don't need to go to a handset vendor and says, I need an LTER handset. No, you only need an LTE handset. And that opens up the capability of 3,000 different types of handsets at your disposal.
Okay. Thank you. Thank you very much.
Okay, Ashish, we are short of time and we need to go for our next meeting. Can we close the session, Ashish?
Okay, Ashish, please continue.
Okay, sir. Thanks, Mr. Mayank Bhargav ji, Mr. Praveen Wadhwa ji, Mr. Ashish Sharma, and Mr. David Rothbaum for the excellent presentation. And I also thank all the dignitaries and participants for giving their valuable time for this webinar. We hope that the webinar will serve its purpose and will benefit the S&T Department of Railways. Now I will request Director S&T Chemtech to address the participant and to conclude the webinar. Sir.
Okay, thank you, Ashish. First of all, my sincere thanks to Mr. Mayank Bhargav that उन्होंने busy schedule में से हमारे लिए time निकाला and he has given and his team has given very good presentation, a wonderful presentation I should say, and I think more or less all the questions they have taken up. So I sincerely thank Mr. Mayank and his team for this wonderful presentation. I also thank all the dignitaries for joining this session. Again, next week we are going to have one more presentation, and that is based upon the functional testing of EI based of this QSON based EI. So I thank you all for joining the session, and I'm sure we must have got educated about these LTE networks. And once again, I'm thanking Mr. Mayank Bhargav and his team. Thank you. Thank you very much.
Thanks, Vijayji. Thank you very much for this opportunity. And it has been a pleasure to connect with you and Ashish. And once again, thanks for everyone to join and spending almost more than 2 hours with us. My sincere thanks to David, Praveen, Ashish, Shalini. They have been excellent speakers, and the deliveries have been fantastic. Ashish, if you don't mind, if you can share the video recording of the session with me, that would be very kind enough.
Okay, sure, Mayank ji.
Thank you very much. Have a good evening, and thank you very much. Have a nice weekend.
Thank you.
Bye-bye.
Thank you very much. Thank you.
Thanks.
Thank you.
Thank you.
Thank you.